Welcome back to the Big Picture Podcast. This is the Do the Review segment for Chapter 4.
What's Chapter 4 on?
Subatomic particles.
Cool. What's the main idea?
Main idea? Well, atoms, you see, they're made out of electrons, protons, and neutrons. Those are the subatomic particles.
All right. Chapter 4, Subatomic particles.
First, quick note, we are here in Chapter 4, but this, of course, is Episode 5, because there's quite a bit of material to cover. We're just splitting it up into smaller episodes. So for this next episode, Episode 5, we'll be doing the first half of Chapter 4, and in Episode 6, we shall get into the heavy second half of Chapter 4, quantum mechanics. You ready?
Let's do it.
Section 4.1, Physical and Conceptual Models. What's a model?
Something on a different scale from what we're talking about.
Okay, so you're thinking like a toy airplane is a model of a real airplane, right?
Mm-hmm.
So what you're looking at there is what we call a physical model. It's simply the real thing built on a different scale. You're just reproducing the physical structure on a scale that you're able to hold in your hand or appreciate better. So that's a physical model. We're not talking about physical models or in chemistry. Our focus is on another type of model we call the conceptual model. Tracy?
So the conceptual model has to do with actually modeling how something works, how a system works.
Behavior. So think of the weather.
Okay, so we can have conceptual models on the weather that help us determine if it's going to rain or snow or be sunny.
So the conceptual model describes how all the different components within the system are behaving. And if you can understand the behavior of that system, then you're in a position to be able to predict future behavior of the system. Think of a hurricane.
Mm-hmm.
So a good conceptual model of how a hurricane behaves allows you to predict where that hurricane might make landfall. So we distinguish a physical model from a conceptual model. A physical model just replicates it on a different scale. A conceptual model actually describes how the system behaves. And so here's where we have to get something out of our heads. We know atoms are really, really, really small. And we're tempted to want to ask the question, well, what does the atom look like? We're going to want to build a physical model of what that atom looks like. Well, it turns out the atoms are smaller than the wavelengths of visible light. So the very question of what the atom looks like is not really something that makes sense.
Why is that?
You can't see it. Even with the most powerful optical microscope, the light passes right by it. And so you say, well, let's use shorter wavelengths. Let's use X-ray. As soon as you use X-ray, you zap it from where it was. It just boggles the mind. It's not something you can see because it's too small to be seen. So the idea of using a physical model to replicate the atom, which is ultra, ultra, ultra small, it just doesn't make sense. But really, we need to ask the question of why would you need that physical model? You really want to be able to predict the behavior of that atom. And so rather than a physical model, really what we need is a conceptual model of that atom. Consider it's a system, just like the weather is a system of different components, humidity, wind speed, temperature, atmospheric pressure. The atom is a system of subatomic particles, electrons, protons, and neutrons. There's electromagnetic forces. There's what we call a nuclear force. How do all those components behave together? And when you got that, you're going to be able to predict the behavior of that system, of that atom. And that's what we really want. Because once you understand how the atom behaves, you can control it. And that's what we call chemistry.
I'm wondering, not only is the atom too small, but the atom starts crossing over into different behaviors. So that's when we're looking at
quantum mechanics.
Right, that it's hard to create a physical model, not just because of its size, but it seems to me it's more because its behavior is falling in and out of the physical material realm between light and waves and energy.
Excellent. It's crossing into the energy realm. And what we'll be talking about in this Do the Review when we get into quantum mechanics is exactly that. The atom is not a hard, tiny little particle thing that you might think it is. It's an interplay between mass and energy. Ooh.
So as soon as we create a static form or a model of an atom, then it's just a very limited...
You're on the particle side of the equation. The reality is there's the energy side of the equation too. Oh. Can we talk about it right now?
Let's move forward. Go ahead.
No, we hold ourselves back. We'll get there. Let's talk now about a little bit of the history, right, of how we got here in the first place.
That seems really important, especially in learning how other people learned.
So section 4.2, the electron was the first subatomic particle discovered. This whole notion that there are these things called atoms put forth by Dalton in the early 1800s was quite difficult for people to accept. Remember the idea of if you have particles, that means you have nothing in between the particles but empty space. So that was a big question of the 1800s. Well, just as they were solving that question of whether elements are made out of these tiny particles called atoms, along came evidence that there was potentially something even smaller than the atom, and that totally freaked people out. They're having a hard enough time accepting the idea of atoms, let alone particles that are even smaller than atoms. Yet that was a discovery that started with, J.J. Thomson in the late 1800s. So J.J. Thomson worked with the cathode ray tubes, and you'll see videos of that at Conceptual Academy. And long story short, those cathode rays within those tubes were just a beam of these tiny particles called electrons. And of course, it was also with the work of Millikan, Robert Millikan. His evidence and the evidence laid out by J.J. Thomson, put those together, came up with the idea that you have something that has a mass less than that of the smallest known atom, hydrogen.
Okay, wait. So just for entertainment's sake and for lubricating our conceptual imagination, can you describe the oil experiment?
Okay. So you know those little perfume bottles that your mom had when you're growing up?
Maybe grandmother or great-grandmother?
Great-grandmother, like that, and it sends out a mist. That's called a nebulizer, and you're just basically pumping air through a liquid, pushes the liquid through a tiny little nozzle, and it spits out these tiny little droplets. That's what Millikan did. He had a little nebulizer, it's called, and he made all these little oil droplets. Now, the thing is, the oil droplets kind of float through the air, like a cloud, but they would slowly drift downward. They would drift through a little hole in a metal plate that he had charged. And as those little tiny oil droplets would fall through that hole, they would pick up a charge, let's say a negative charge. And then he would take the charge of that plate and flip it. And so those tiny little negative charged oil droplets would suddenly be attracted to a charge that was above them because they've already passed through that little hole. So the poor little oil particles are in a conundrum. There's gravity pulling them downward, but there's an electrical force of attraction pulling them upward. You can see what Millikan could do is he could play around with the strength of the electric force. He couldn't play around with the strength of the gravitational force, but he could play around with the strength of the electrical force, and he could make some of those oil droplets hover because he could make it so that the electrical force upward matched the gravitational force downward. So he was able to make those tiny little oil droplets hover. Are you with me so far?
Okay, so these little oil droplets they're getting sprayed into a container. They're falling through a metal plate, a hole in a metal plate. And as they go through that plate, the plate is charged. So they pick up that charge and they continue to fall after they go through that plate.
Yeah.
And then Millikan will change the charge of that plate. The polarity. So rather than it being a positive charge, say, which the little oil droplet now picked up a positive charge, he would change it to a negative charge. So now the droplet is falling, but suddenly it has a new attraction to that negative charge.
Upward
On that plate. Is that right?
You got it. Excellent. And so he could play around with the degree at which that plate was charged, and he could get different droplets to hover, because some droplets were heavier, some were lighter, right? And what he did is he took the readings of the charge, of what it would take to make one of those droplets hover. And so he took tons of readings of how much charge was needed to make them hover, and he noted something very unusual about the numbers, the reading on the charge. They were like numbers like 5, 10, 15, 50, 45, 65, 75. What do all those numbers have in common? 105, 95, 90.
Divisible by 5.
They're all factors of 5. Likewise, he looked at all those numbers. They weren't factors of 5. It was factors of something else, but he found it was a factor. And turns out that number he came up with was the fundamental charge that you can possibly have. It was a very tiny amount of charge, but it was a fundamental unit of charge that he came up with. And knowing that fundamental unit of charge, he was able to backtrack to J.J. Thomson's experiment to calculate the mass of one of the tiniest particles, known as the electron. And its mass was found to be less than that of a hydrogen atom, which just blew people's minds.
Wow, fascinating.
Yeah. Okay, so there we go. Some history in terms of the discovery of a subatomic particle.
I think it's really important and fascinating to see something that seems like, what is he doing? He's just passing oil droplets through a plate, but that he kept taking it further and further and was able to really add to our understanding of the phenomenal world.
I see creativity. I see analytical thinking. I see
endurance.
Yeah, just persistence, just going after it. The drive. Wow, a hero. Section 4.3 goes into a little bit more history. Ernest Rutherford discovering the atomic nucleus. Okay, so now we have this idea that there's subatomic particles. We're talking about what the structure is of the atom, right? Keep in mind, physical models versus conceptual models here. What Rutherford did was he had a tiny, thin gold foil. The property of gold is that you can pound it to very ultra-thin sheets. It's so thin it can be just several atoms thick. And what he did was he passed these particles called alpha particles, which were actually much larger than a hydrogen atom, but they were known particles from radioactivity, which we'll talk about in the next chapter. He directed these alpha particles through this thin gold foil. And he expected that the alpha particles, because they're so large and massive, would just plow right through those gold atoms. And indeed, they did, mostly. But occasionally, one of those alpha particles would bounce off of those atoms in a reverse direction. And that freaked him out. It was, to him, akin to firing a cannonball at a paper tissue and the cannonball bouncing backward. What did that cannonball hit? The cannonball, of course, being the alpha particle, and the tissue being the very, very thin gold foil. Well?
So I want to just ask a question.
Mm-hmm.
As you say, he has a source of alpha particles. I wouldn't know where to get a source of alpha particles. I don't even know what that is.
Okay, understand when one is making discoveries, they're not doing it in a vacuum, per se. There's prior knowledge. By the time of Rutherford, there had been work with Madame Curie in this realm of radioactivity, learning that some elements emit these particles that can be harmful, that can do bizarre things. So at that time, Madame Curie had done a lot of her work with radioactivity, and what was found is you can have these materials like radium is an element she discovered that's emitting this radiation, and one form of that radiation is these tiny alpha particles. So what Rutherford did was to shoot alpha particles at the gold foil. He took a lead block and drilled a hole in it and dropped some radium, I think it was radium, at the bottom of that little hole. It was naturally shooting out alpha particles. Well, because it's at the bottom of a hole, the alpha particles are just going to shoot straight up outwards. And so essentially he made himself a little alpha particle gun.
Oh, okay.
And he pointed that toward the gold foil. And how are you going to see whether the alpha particle's passing through it or not? And he put around a fluorescent screen, because whenever the alpha particle would hit the screen, you get a little blip, right? So there's the idea of fluorescence, which was also known about by this time. And so you see, he's taking previous discoveries and using them. And of course, in this way, science builds upon itself.
Then he starts measuring the angles that the alpha particles go through.
And his only conclusion was that most of the mass of an atom is concentrated in its center. He discovered what we now call the atomic nucleus. And it's said like this: if an atom were the size of a baseball stadium, the nucleus would be like a baseball on the pitcher's mound. Mostly what you've got is empty space. If you want to find where the mass of the atom is, it's on the pitcher's mound in that tiny little baseball. As small as a baseball is to an entire Major League Baseball stadium, is as small as an atomic nucleus is to the size of the atom. The atom, he discovered, is mostly empty space. Its mass is concentrated in yet another particle at the center, which was dubbed the atomic nucleus, the atomic center.
Okay, so now we're going to learn some vocabulary.
Oh, we're looking now at section 4.4. We've introduced the electron and the atomic nucleus. Let's just cut to the chase and point out how it is that the atomic nucleus itself is made of even more subatomic particles. They are the
protons and
the neutrons. Here's a generic term for you. Ready? Nucleon. What's a nucleon?
Proton or a neutron.
So a nucleon is any subatomic particle found within the nucleus. Two examples are the proton and the neutron. So the atomic nucleus is made out of nucleons, and there are two types, the protons and the neutrons. Ooh, vocabulary.
Okay, so what is a neutron?
Neutron, as its name implies, doesn't have an electric charge, which in fact is why it wasn't discovered till later. It was neutral. It wasn't behaving within electric fields, right? And it would just slip right on by. It was Chadwick who discovered the neutron. That's another story. The neutron is neutral, and the proton carries a positive charge. And we get to talk more about why we have protons and neutrons in chapter 5. It's fascinating. But for now, we're just looking at what is there in the atomic nucleus, the protons and the neutrons.
So at this point in our vocabulary, we would call a proton subatomic particle that carries a positive charge.
It's a nucleon. It's a subatomic particle. It's found in the atomic nucleus. Ooh. And it has a positive charge.
So that is the definition of a proton?
Yeah,
okay.
I like that. And then there's that starts with L. Name 4 subatomic particles, and the students will go, protons, neutrons, atomic nucleus, and I'll say, okay, another one, it starts with L.
Electron.
The electron. The electron has a negative charge. Its negative charge is exactly opposite to the positive charge of a proton. They're equal and opposite in charge. The electron is not a nucleon. The electron is really, 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 really small. The electron has a mass about 1/2000th of that of a proton and neutron. When you think of a proton and neutron, think of these big subatomic particles, like of a unit of 2,000, eh? When you think of the electron, think of this tiny little thing. tiny little thing has a mass of only 1. And 1 is much smaller than 2,000, right? So that's to say the protons and neutrons, they got all the mass. Look where they're located. They're in the atomic nucleus. Well, what about the electron? The electron doesn't have much mass. It has mass, but not much. The electron, however, has
velocity?
Rhymes with volume.
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 That seemed too obvious.
It has the volume. It defines the volume of the atom, right? It defines the volume of the baseball stadium. If the nucleus is the baseball on the pitcher's mound, the electron is a tiny flea that can zip around the entire baseball stadium. Within the atom, the electron is indeed zipping around at high speeds around that nucleus. And as it does so, it sweeps out this volume of space. That is essentially the diameter of your atom. So you get the idea that the atom is mostly empty space. You've got a tiny electron that's moving around. Now, although the electron doesn't have much mass, it does have
charge.
A charge. And that charge extends outward beyond the diameter of the atom. So really, the atom's diameter is defined by the space that the electron sweeps out as it whizzes around that most massive atomic nucleus and dense, tiny atomic nucleus at the center of the atom.
How come it doesn't get any closer to the pitcher's mound? Why would it stay out in the way upper stadium?
You mean the
bleachers?
electron is negatively charged and the proton is positively charged? How come that electron just doesn't right into the nucleus where it's attracted?
Yeah.
It does.
Then what keeps it out in the bleachers?
Quantum mechanics. We're not there yet. We're
Okay.
there. Okay, so in section 4.4, gosh, we've got protons, neutrons, and nucleons, the atomic nucleus. And here's a good one for you. Atomic number.
Okay, pause. See if you can define for yourself. Proton, neutron, nucleon, atomic nucleus. Anything else?
Starts with L.
Electron. 5 things. See if you can define those 5 things right now.
Yeah, it's a vocabulary, right?
Okay.
And then let's add on top of that atomic number. Atomic number, pretty darn important. It's the number of protons in the nucleus.
The number of protons in a nucleus.
Yeah, just count the number of protons there and you have your atomic number.
Just the protons.
Just
atomic
the protons.
number protons.
Yeah, put that on your flashcard. You see, we define an atom by its atomic number. That is to say, we define an atom by the number of protons it has within the nucleus. That's just our convention. So the atomic number is important. It's what we use to define the atom. And you'll see the atoms of elements in the periodic table are listed in order of their atomic number. Hydrogen has 1 proton, so it's atomic number 1. Helium has 2 protons, so it's atomic number 2, and so forth down the line. All right, so hey, let's add even more, shall we?
Okay.
Mass number.
Mass number.
I know mass number sounds an awful lot like atomic number now, doesn't it?
It sure does.
It's
That's
not
another number.
It's not the same thing. So the atomic number is the number of protons, right?
Atomic number is the number of protons.
Mass number is the number of nucleons.
Nucleons, we remember, is protons and neutrons.
Yeah, so you have to add up all the protons and all the neutrons within an atom, and that will give you the mass number. So here, let's do a quiz. Iron 56. Now, you see iron-56. That 56 that you see there is the atomic mass number. Iron 56. Take a wild guess how many nucleons are in iron 56.
56.
How many nucleons are in iron 55?
55.
But wait a second. aren't they both iron?
That's what you said.
Well, if it's iron, how many protons does it have?
Okay, looking at the periodic table, it looks like it has 26.
There are 26 protons in any iron atom, by definition, right? So how can it be that you have iron 56 and iron 55? You see, the number of protons is always going to be the same, which is 26. Here's the key. The number of neutrons can vary.
Okay, so you're telling me that the mass number is the number of nucleons.
Yeah.
And the atomic number of iron is counting just the number of protons.
Yes.
And so the atomic number of iron has 26 protons.
The atomic number is 26 because it has 26 protons.
Got it. So we have iron 56 and iron 55. So there's two different mass numbers.
Yes.
Okay, so there can be different numbers of neutrons.
Yeah, you got it.
In that
iron
atom.
To say there are different types of iron atoms. There are iron atoms that have 30 neutrons in the nucleus. There are iron atoms that have 29 neutrons in the nucleus. They're all iron atoms. They're all siblings. They all have 26 protons, but the number of neutrons can vary. Not for any one atom, but you're going to have an iron atom that has 30 neutrons over here, and then over there, you'll have an iron atom that has 29 neutrons. The number of neutrons can vary. That's all I'm saying.
Okay.
So how do we distinguish between iron 56 and iron 55? They're both forms of iron, but they're different somehow. And that's where we introduce the term isotope. Iso means same. Tope means, I have no idea. But iso means it's the same. They're both iron atoms, right? They're different forms of the same thing. When we say isotope, that's literally what we're meaning. They're different forms of the same thing. That thing here being iron. Iron 56 and iron 55 are both different forms of the same thing. How are they different? By the number of neutrons that they have in them. So we talk about the iron 56 isotope, or we can talk about the iron 55 isotope. They all have 26 protons. The iron 56 isotope has 30 neutrons. The iron 55 isotope has 29 neutrons.
How many different isotopes can you have for iron?
There are a lot of different isotopes, but here's the deal. Some isotopes are more stable than others. Let's simplify a bit and move back down to hydrogen. There are 3 predominant isotopes of hydrogen. The most abundant hydrogen atom we've got is the hydrogen 1 isotope. Hydrogen 1, the mass number of 1, but it has an atomic number of 1. What plus 1 equals 1?
What plus 1 equals 1? Oh, 0.
The number of neutrons in hydrogen 1 is 0. There are no neutrons in hydrogen 1. Okay, so we're simplifying things here. So hydrogen 1 is the most predominant isotope of hydrogen that you'll find in nature. You also have hydrogen atoms that do have 1 neutron. That's H2. Then there are some hydrogen atoms that have actually 2 neutrons. So 2 neutrons plus 1 proton, that adds up to 3. So that's the H3 isotope.
Okay.
So H1, H2, and H3. They all have 1 proton, but they vary by the number of neutrons that they've got. One has 0, the other has 1, the other has 2. Now, what do you have most of? Mostly what you've got are H1. Out of 1,700 hydrogen atoms, you're going to find one of them is a H2. And then there's H3. H3 is really, really rare. Turns out it's also radioactive. It's also known as tritium. H2 is known as deuterium. And H1, they call that protium. Okay, so those are the 3 different isotopes of hydrogen. And we have different abundances of those isotopes. And a lot of that is dependent upon the history of the universe, as well as the stability of the isotopes themselves. H3 is not very stable, so guess what? We don't have very much of it in this corner of the universe.
So 2 atoms are isotopes of each other if they have the same atomic number,
Yep.
but different number of neutrons.
Yep. So that wraps up episode 5, also known as Chapter 4B. What's next?
We'll be going into quantum mechanics.
Ooh, I can't wait.
Just a heads up, listeners. Make sure that you listen after a good night's sleep.
You mean no cramming late at night the night before the exam?
No way.
Thanks for listening. Our theme music by Zach Jeffrey. Musical flourishes by and in memory of Charles Paxton. For more of his music, look for Charel, that's CHAR-EL, at places such as Spotify. Production assistance from Greg Simmons and CPro Music. For show notes and more, please visit conceptualscience.com. A note of appreciation to all instructors using Conceptual Academy. Thank you for your support. And to the hardworking student, our thanks to you as well for your learning efforts, which we see as the path to making this world a better place. There's a bigger picture. That's good chemistry. Till next time,
Good chemistry to you.